Hello and welcome. This video is going to explain the answers to the Chapter 10 practice test. The first question is just asking about the null hypothesis here and the symbol you use for that, and that's rho, this little thing that looks like a p, but it's rho. And the null hypothesis is always that the rho is going to be equal to 0. In other words, the two variables that you're talking about are not correlated with each other. This is like a mu for a mean. For a correlation, it's like a rho. Next question, we want to generate the scatter plot between a belief in just world and depression. So I'll go over and I'll do everything that you need to do for, almost everything you need to do for the correlation. So we'll do regression, correlation matrix, and then we need a correlation between just world, belief in a just world, and depression, so we'll throw that over. It's always good to get n, and you'll need the confidence interval around n. And we can get a scatter plot, excuse me, by clicking on that. And that'll give you generally enough information to look and see if it's problematic, if there's anything in the scatter plot that makes it look nonlinear or heteroscedastic or anything like that. And this looks pretty linear, so it looks like we're good to go. And so we have pretty much everything we need right here. So let's go ahead and answer some of these other questions. So we've generated the scatter plot, and does it look like it's sufficiently linear? Yes, it does. It looks fine. If we wanted to get a better picture, we could get a scatter plot doing it this way. It'll just give us a bigger picture of the analysis. And again, it doesn't look like it's nonlinear. It looks like there's a linear trend. So we should be good to go. Now we want to find the Pearson's correlation. Well, correlation between belief in just world and depression is right here. The p-value is right here. The r squared is not given to you. You have to compute it yourself. So if you take the r and just square it, you will get the 0.33. And then the interpretation of the effect size of correlation, which is, again, r squared, is this first one. It's the percent of the variability in the dependent variable, in this case, depression score, that is explained by belief in the just world. So if you know, it's basically how much overlap there is between the variance in the two variables, and it's going to range between 0% and 100%, and a overlap, or an r square of 0.33, is considered a large effect. Again, the cut lines for r squared are 0.01 would be small, 0.09 would be medium, and 0.25 would be large. That's for r squared. Now, you can find the table for that on page 390 of your text. And then you need the upper bound and lower bound for the r, and here they are. And then you need to report all of the statistical information, and you'll need to get the means and the standard deviations for the variables, each of the variables independently. So we don't have that yet. So you want to go to Exploration, Descriptives, and you can just pop both of them over there and make sure you're getting the mean and the standard deviation, which you are. And so now you have the mean of each variable and the standard deviation of each variable here. And you can use that information to answer these questions over here. The number in the parentheses is the degrees of freedom. That is n minus 2 for correlation. So we have an n of 100, So our DF is 98. And then after the equal sign is the actual R, and then of course your p-value, and then your upper and lower bounds. Now the interpretation. Overall, a greater belief in a just world is associated with higher depression scores. Why do I say higher? Because it's a positive correlation. So as one variable goes up, the other variable goes up as well. So a higher belief in a just world is associated with higher depression score. And there was a strong evidence against the null because this p-value is so small. And the effect size, again, as I said, was large because the cut line for R squared, something close to 0.25, is large, and this was 0.33. Are these results consistent with the literature? Yeah, if you read the first description of question 1, it said that previous research did find an association between belief in a just world and depression. So we kind of replicated that effect. So this is consistent. The next question asks us to analyze a relationship between two different variables. So we'll need to go back to here. It's talking about belief in a just world and attitudes towards the poor. So we need to run a different correlation. So we do correlation matrix again. Belief in a just world and attitude toward the poor. We want to get n, and we want the confidence interval for n. And again, we can get the correlation matrix this way. And it looks, again, it doesn't look like there's any nonlinearity problems, so I think we're good. And so now we can just fill out our information. Again, we would need to get the mean and the standard deviation for these variables individually again. And again, you would do that by getting descriptives, popping over the two variables you're interested in, and then you'll get the mean and the standard deviation over here. And that'll help you fill out these blanks. Now to go back to the R information we need to fill the rest of this out. You can see, again, we have 100 people, so the DF is 98. Our R is provided for us right here. Our p-value is right here. Our upper and lower bound are right here. Now the interpretation. Overall, a belief in a just world is associated with a more negative attitude towards the poor. And we say that now because it's a negative correlation. So as your belief in a just world goes up, your attitude towards the poor is more negative. It goes lower. So that's why it's a negative correlation. There was strong evidence, again, because the p-value is very small. And it's medium because if we square the correlation of 0.26, we're going to get something that's closer to the medium cut line for the effect size of R squared, which, again, the medium cut line, something close to 0.09. So if we square 0.26, and we square that, you'll get a 0.07-ish. So again, that's about a medium effect. And now we're going to interpret the scatter plots. And you got to match it up correctly. So this kind of looks like it has a slight positive trend in that a lower score on one variable is associated with a lower score and a higher score with a higher score. But it's not a real strong relationship. It kind of more looks closer to a ball than it does a flat or ellipse. So it's positive and it's a weak relationship. So the 0.23 is probably your best choice. This one, again, is a positive relationship because it's sort of leaning to the right. A lower score on X is associated with a lower score on Y, and a higher score on X is associated with a higher score on Y. But it's a much tighter line, so you're going to get a stronger relationship here. So it's positive, and a 0.8 is the better choice because it's such a tight line. And then here's another example. This is a negative relationship because, again, it's a higher score on X is associated with a lower score on Y, and then a lower score on X associated with a higher score on Y. And it's not a super strong relationship. So a 0.6 would be too strong. 0.3 is, again, you just get used to visualizing and seeing how close to a ball versus how close to a line these things are. The stronger it is to it, the closer it is to a line, the closer the correlation is to 1 or -1, and the closer it is to a ball, the closer it is to 0. Okay. In this question, which of the following would be the best predictor of GPA? Basically, you want to find the R that has the highest absolute value. The negative doesn't matter. You can predict a score between two variables, or the relation. You can predict one score from another score, regardless of whether the correlation between the two variables is positive or negative. And your prediction is going to be stronger or more accurate if the stronger the correlations, regardless of whether it's positive or negative. So you're just looking for the R that is the highest absolute value. If you look at this, this scatter plot is problematic. If you saw something like this, you wouldn't want to run a correlation that you know because it has something that's called heteroskedasticity. If you look at the variability on this X score, X goes on the bottom, of course. If you look at the variability on this X score, it's a fairly small amount, but if you look at the variability along this X score, it's a much larger amount. So there's more variability in Y for these X's than there is variability in Y for these X's. That's called heteroskedasticity, and that's a problem. So when you see something that looks like that, and of course it can be, the more greater variability could be over here, and the less variability could be over here. It doesn't matter which side it's on, but it just matters if you have roughly about the same across the whole values of X. And we do not have that here, so this is heteroskedastic. Now, when do you want to run a Pearson correlation? There's two ways that would be the thing to do. One, if again, a correlation is looking at the relationship between two variables. If one or both of the variables that you're measuring are ordinal, they're measured on an ordinal scale, then you're going to want to use a Spearman. Or if the scatter plot is monotonic, and a good picture of that is on page 384 of your text, the middle one. You can see it's sort of a curve in that rather than a straightish line. It doesn't fold on itself like the picture on that page 384 on the far right. It sort of folds over and waves on itself. You don't want that. It just has a gradual bend. If that's the case, then that's a scatter plot would say that you can use a Spearman correlation, and you should. Okay, so effect sizes are rarely reported in APA. Why? Because really an R is its own effect size, and it's very easy to just take R and square it to get the R squared interpretation. So that's really why. It's just super easy for people to do it for themselves, or they can just think about it in terms of cut lines for R. A correlation of 0.1 would be considered small. Correlation of 0.3 medium, and a correlation of 0.5 would be large. So you could just use those cut lines for R rather than the previous cut lines I gave you for R squared. They're exactly the same. Okay, so now it comes to the picking the right test statistic. We're going to go over a lot of examples in these in the review day, but I'll go through these as well. So in this case, we have just one sample of people, and we're comparing their score to a set score of 100. And so and we do not know the population standard deviation. So we have just one sample mean. We're comparing it to some other score, and we don't know the population's standard deviation, so it's a single sample t. this example is a correlation. People are taking two different surveys, and each survey yields a score, the score can be a range of values. So it's not a category that you're getting from each survey, it's a range of scores measured on an interval ratio scale. So if both measures are measured on both scales, surveys are measuring an interval ratio variable, it's going to be a correlation. In this example, we have two groups of people, and we're comparing those different groups of people on some independent variable that's measured on an interval ratio scale. So that's why it's an independent t-test. Here is a related samples t-test, again, because we're measuring the same group of people twice. So we're just taking a measurement of blood flow. We're measuring it before they exercise, then we're measuring the same people again afterwards, and so that's a related samples t-test. And here we have another correlation. A little bit more complicated scenario here, but what they're measuring here is the time that it takes people to make a judgment between two animals that they're given. So if I give you the words pig and wolf, how long does it take you to say which one's bigger? And then sometimes, so that's one variable, the time it takes people to make their judgment. The other variable is the size difference between the two animal examples I give you. The size difference in real life between a pig and a wolf is relatively small, certainly much smaller than, say, which is bigger, a roach or an elephant. So here we're measuring how quickly people make the judgment based on the relative difference in these animals in the real world and how long it takes them. That correlation between that and how long it takes them to actually make the judgment. So again, both of those variables are measured on an interval ratio scale, and so that makes this a correlation. It would specifically be a Pearson's correlation. And this other example has two factors. The first factor is whether you're making chocolate fudge or vanilla fudge. That's one factor. And the other factor that you're dealing with is whether you're using real vanilla or a cheaper vanilla extract. So those are the two factors, whether you're using real vanilla or fake vanilla. And then whether you're making chocolate fudge or vanilla fudge. Who knew that there was such a thing as vanilla fudge? But what are the two factors you're making? And then the dependent variable is how much people like what they're tasting. So this has two factors with one dependent variable measured on interval ratio scale. So that's a two-way ANOVA. And it looks like the last question is a one-way ANOVA. And here we have three groups of participants. We have a group of rats that are a control group and they don't have any area of their brain removed. A second group that has 10% of their hippocampus removed, and a third group that has 20% of their hippocampus removed. So those are the three groups, and then they perform a maze and their number of errors are counted. So again, we're trying to see if the amount of brain tissue removed is associated with the number of errors. And we have three groups, and the independent variable is how much brain area is removed, and the dependent variable is errors. And again, we have three different groups, so it has to be a one-way ANOVA. Okay, we'll talk more about picking the right test statistic in class. And if you have any more questions about anything else in the correlation chapter, obviously talk to your instructor.